Hello everyone, today we're going to be working on problem 4.158, and this problem is saying that the distribution of soil loading on the bottom of a building slab is shown. Replace this loading by an equivalent resultant force and specify its location measured from point O. So we have point O right here. From there, we have 50 pound-feet being the smallest weight on this side. Then we have the maximum weight of 300 pound-feet right here, and then we have 100 pound-feet on this side. As you could see, we have this type of shape, and it's asking us to determine to replace the loading by an equivalent resultant force. So to do that, what we're going to do is we're going to be cutting this shape right here in half. And that way we know that this shape is 12 feet long and this shape is now 9 feet long. And then from there, what we're going to do is we're going to be cutting both of these shapes into a right triangle and a rectangle. We're going to be cutting it at that point 50 all the way across. And then on this one, on the right side, we're going to do it from this point 100 all the way across. So now that we have these four shapes, 1, 2, 3, 4, we're going to be finding their forces individually, and then from there determining that overall resultant force. So what we're going to do first is we're going to call this area 1. Then from there, we're going to call this area 2, area 3, and section 4. So to find force 1 or R of 1, we know that it has a constant loading of 50 pound-feet for a span of 12 feet. So we're going to multiply those two together, giving us a force of 600 pounds. Now for shape number 2, we know that it's a right triangle, which is why we're going to be using the formula half, 1/2 of the base times the width. So for here, we know that it has a span of 12 feet. And now from there, to determine the height of this side right here, what we're going to do is we know that the highest point used to be 300 pound-feet, but then from there, we're subtracting from the 300 pounds the 50 pounds, which are now just included in the right triangle, giving us that now the highest point or the maximum weight on this right triangle is 250 pound-feet. And that should give you 1,500 pounds. For force 3, we know that it has a span of 9 feet with a constant loading of 100 pound-feet. Giving us 900 pounds in force. And for the second right triangle, we're going to multiply that again by 1/2 of. This time, we're going to be subtracting 100 from 300 to determining that maximum weight, which is 200 pound-feet. And that should give you 900 pounds as well. So now that we determined the force for each of those shapes, what we're going to do now is we're going to determine each of their locations exactly from point O. So for the rectangles, we know that since it's a constant loading, that's going to be found exactly like mid-span of their lengths. So we're going to do that first. So for force 1, we know that it's exactly mid-span of 12 feet. So we're just going to take 12 feet, divide that by 2, giving us 6 feet from point O. Now for force 3, we know that the force is going to be found right here mid-span. So half of 9 feet is 4.5 feet, but then we're going to add this 12 feet. So because it's going to be this far away. So we're going to add those 4.5 feet from here plus the 12 feet, which should give you, so let me write that. 9 divided by 2 plus the 12 feet should give you 16.5 feet. Then from there, we have our two right triangles. And if you guys remember that when it comes to a right triangle, the force is always going to be 1/3 away from the highest point of the triangle or 2/3 away from the lowest point of the triangle. So for our first right triangle, our section 2, we know that that force is going to be right here. So from point O, it's going to be 2/3 in of that triangle. So the location of force 2 is 2/3 of 12 feet, giving us 8 feet. And for force 4, from point O, it's going to be all of this 12 feet plus, since the highest point of the triangle is right here, then that means that it's just going to be 1/3 in, because it's going to be right here. So it's going to be 12 feet plus 1/3 of the 9 feet span. So 9 feet times 1/3 plus the 12 feet. And that should give you a total of 15 feet. So with that, we determine each of the forces and their locations. But now we have to determine or replace the loading by an equivalent resultant force and then specify the resultant force's location. So to determine that resultant force, we're just going to sum all of our forces. So F of R is equal to the summation of our forces. So F1 plus F2 plus F3 plus F4. So our resultant force should equal 3,900 pounds. And we know that that force is going to be applied upwards. And now for our location of our resultant force, we know that we could determine that equation by writing, if we were to take the sum of the moments about point O and looking at this, point O is on the left side. We know that our resultant force is going to be somewhere here on the right side, and it's going to be going upwards. So that means that it's going to be causing a counterclockwise moment, meaning that it's going to be a positive moment, what it's going to be creating. So we know a positive moment, and we know that a moment is equal to the force times the distance. Our force is our resultant force in this case, times our distance, and our distance is that location of our resultant force. And we could rewrite this simply by putting F1 times X1 plus F2 times X2 plus F3 times X3 plus F4 times X4. Remember, all of these are positive moments because they're also on that right side of point O and they're all pointing upwards. So we know they're all going to be creating that positive moment. We have our forces that we already found. And then from there, remember that a moment is force times the distance. And we already found that distance of those forces from point O, which is why we did that since the beginning. So now that we have that, we're going to, since these two are equal to each other, we're going to be rewriting it in terms of just for our location of our resulting force, giving us that the location of the resulting force is equal to negative F1 times X1 minus F2 times X, sorry, not negative. I'm sorry, which means that the location of the resultant force is equal to F1 times X1 plus F2 times X2 plus F3 times X3 plus F4 times X4 all over our resultant force. And you simply just plug in everything into that. So for our top part, we should end up getting 43,950 feet all over our resultant force, which is 2,900 pounds. So that means that our location of our resultant force is 11.3 feet away from point O. And just like that, we were able to replace the loading with an equivalent resultant force. And we also determined the location of that resultant force from point O. So once again, what we did here is first we simply split this shape that was given to us in half, because that way we would know that this shape right here has a span of 12 feet and this shape right here has a span of 9 feet. From there, we split both of those shapes into a rectangle and a right triangle to then be able to determine the forces of each of those shapes. And then from there, we determine the location of those forces from point O, because from there, we found our resultant force. And then from there, to determine the location of our resultant force, we use this equation right here. We simply plug that in, and that gave us that location of our resultant force from point O. Thank you guys so much for watching this video. Please feel free to like this video and subscribe to our channel if you guys would like to see more videos like this.